Okay, here we'll do another example, and this one I'm just going to walk through it again. This is an example by parts of this piece, and we're going to find for the mass moment of inertia about the x, y, and z axes for homogeneous solid piece shown. And it's 7,850 kilograms per cubic meter, which turns out to be a number you see often for steel, right? So this is a little steel piece, and one of the first things we're going to do is figure out what the actual mass of the piece is. We'll call a main piece right here. We'll call this 1, and we'll call this guy right here that we remove, we'll call him 2, right? So we're looking down at the thing right here is the y-axis and the x-axis. Okay, so here's the x dimension, y dimension, z dimension for parts 1 and 2. So we'll see that we have, I did it in meters, so 0.4 in the x direction, 0.4 in the y direction, and it's going to be 0.1 or 100 millimeters in the z direction. And the same thing is true for the smaller square that we're removing. And we can get the volume by just multiplying all three times each other and multiplying that by our 7,850, we get the kilograms. And we subtract the little square from the big square, and we get that total. So that's our mass right here. Now they want it for the x, y, and z axis, so it's good to do this and draw this thing out. So looking down the x axis, here's a big creepy eye, and we're looking down the x axis. This is what we would see, and you could see that this right here is where part 2 is going to be. Right here, part 2 is right there. So we set up our grid here, our table, and with we already had mass from the previous table. I have my y and z dimensions that I brought back. The y and the z are the only one that matters, and the incremental incremental, the mass moment inertia for the parallel rectangular prism, I guess you'd call it, right here about the x direction is going to be 1/12 the mass times, in this case it's going to be the y squared plus z squared. And remember that x is out of the board, so this is actually like we're going to spin it about the x-axis. That's the moment of inertia that we're looking for right there. So there's parts 1 and 2. Bring the mass over. Here's the dimensions for this. And so applying that part mass moment of inertia. And now we want to, but that's both of these right here are about this axis. Well, let me say, okay, so sorry about that. Let me move my picture. Don't even need to see me. I don't know why I put that in there. Maybe we could chart my facial hair growth over time. Okay, so for 1 right here, here is the center about which we're taking it. That's what this moment of inertia is going to be. But we want it to be over here, right? So it needs to move 0.2 in the y direction. Remember, that's the y direction, so it needs to move over 0.2, and then it needs to move down 0.05. So it's actually moving along that line right there. That's the distance that it needs to move. So right now, with this moment of inertia, it's spinning about this axis, but we want it to spin, I don't know why I drew them in different directions. Instead of this axis, we want to draw about this axis right here. So it needs to move, and it needs to move with the parallel axis there. So this guy right here, he's just the square of the square root of the square of these two terms, and we can add this squared right here times this incremental mass, and also add in the I said incremental again. It's for that big block, for the larger of the two. So that's what its mass moment of inertia is of a big square about the x-axis. And we do the same thing for part 2 right here, but now in this case right here, we're going to be moving, oops, where did we go? Somewhere in here, right? I think it's this guy. Yeah, okay. Sorry about that. Yeah. All right. So what I was trying to do was change colors right here so that we could actually see. So now this one, that's the part 2, the missing part. It's going to move from that spot down to here, right? So it's got its own distance d that it's going to move. It's going to use 0.1 over to the left, 0.05 down, and then you'll have this distance, and then we will end up with that as the mass moment of inertia. But again, it's subtracting that out. But what we had to do first, though, we had to use the parallel axis theorem to get them so they shared a common axis, and then we could subtract one from the other. We have a similar thing for the y, about the y. It's almost identical, except the location about which that we're removing the thing. All right, so it's going to be about, this is the axis that we want to do it about the y-axis, and we're looking down at with the creepy eye from this direction right here. By the way, my dynamics instructor used to call this the big eye, and I always thought it was creepy, so I was like, I'm carrying on Don Paquette's legacy here, but I'm calling it the creepy eye, not the big eye. He says, you need to use the big eye. And he would draw an eyeball up on the screen all the time. The screen up on the blackboard. That's how old I am. And we put together a table, and in the same way, parts, bring the masses over, get the dimensions, get the individual moment of inertias about here. And looking at this one, it's actually about here, right? That's going to be part 2, is over on the left-hand side. So now the distances that they have to move are different right here. So that's the real fundamental difference here. And then you get the masses right here. Not the masses, but you get that the distances, and you find out what the moment of inertia are. Here's an important thing. All right, so it's almost better that we would have this separated. I did this in one column. Sometimes I would actually break that down into separate columns. But look what the moment of inertia is about the big block, right? Let's just forget that we've even removed this thing right here. But it's a much, much larger number, right? It's after it gets moved. The act of moving it away from its centroidal, or I should say center of mass axis right here, has a big effect on the mass moment of inertia. And in fact, in some cases, when you move it at great distances, you can even kind of neglect. We're not gonna, but you actually will see that in some books or some papers and that kind of thing. When calculating these things, that something could be be like maybe a thin thing that's doesn't really count for all that much, but as soon as you move it away from its own center of mass to a new global center of mass, when you go to construct things together, it has a much larger effect. And remember, that's just like the dude with the weights, right? As you put them outwards right there, and you spin, and then you bring them in, right? That the act of moving it out doesn't just affect it; it affects it by the square of the distance. So that's an important thing to look. But we find a different value, and that's all well and good. And then the last one, it's just more of the same. I don't know why I bothered with doing all 3 axes. I think actually I was copying somebody else. Another instructor was using this as the example, and I just followed suit. But this case, it's going to be about this z-axis right here that we're going to be spinning the thing. And so set up our table, blah, 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 and we get 10.05. Okay, that's all well and good. Here's a SolidWorks example, a representative one. But let's recreate this, actually. So I never checked in my other video whether this thing will show through when I go interesting. I don't know. Let's see. When I go to this remote login thing, hey, my picture stayed in there this time. I don't know why. But I set this thing up and get a new thing. And do I want to make millimeters? I think I want meters. So let me go back to. Let me change the units to meters. And let me see which. I'm gonna take a look. I know I have it on the other page. But let me take a look at what's the orientation there. I'm looking down the z-axis. And now I put my picture in the wrong spot again. I'm looking down the z-axis here. So if I want to, I'm just going to turn this thing around here. Orient this. I want to draw it in the YZ right here. Okay, so here's how I want to draw it, like this right here. So I create a sketch. Is this a new part? Why is I hate this stupid little thingy here. I'm going to get rid of them. Where the hell? I have evaluate and features, but I don't see a sketch. Is that because I'm not in a sketch right here? I don't know. What is going on here? Let me move this thing a little bit. There it is. It was hidden behind that stupid little bar thing. I hate that thing. But I got it with my new microphone. I don't know if I'm digging this microphone or not. Anyway, I make a sketch, and of course it rotated this stupid thing. So now I got to think my way through this. Actually, let's see. I think if you click an arrow, it rotates about that axis. If I hold down, no, it just shifts. If I hold down Alt, there you go. I can rotate this way, and I want X going downwards. Just so I don't have to think, because I don't feel like thinking. Okay. So let's see. Did I draw that onto the other one? Oh, all right. Losing my mind here. All right. So, yeah. I'll just draw it like this right here instead of like adding and subtracting things. All right, you hover and make that guy there. Like that. And I think I got it. No, I probably should have added the relations in there, but I got lazy. And so this guy right here is 0.04, right? And this guy should be 0.04. And this should be 0.02. And then last one, 0.02. And it looks like it's all black, so it's all fully defined. Let me put that up there again and go, okay, I'm okay with the sketch. Now I grab that sketch and I can extrude it. It's going to be 0.05. 0.05. Let's see, it's 100 millimeters, so that'd be 0.1. So 0.05 seems a little big to me. Yeah, I think I did something wrong. 0.05 in that direction and 0.05 in that direction, and I did do something wrong with my dimensions here. So let me see what I did. I'm losing it. What did you do? I don't know. What did you do? I don't know. Let's fix it. Okay. Okay, I see. All of these should have been 0.4. Yeah, and that should have been, come on, baby. There you go. 0.4. Boom. And then this guy, he should have been 0.2. And he should have been 0.2. All right. All right, that looks like the right thing. Okay, cool. And let's see. We could make the material plain carbon steel. That'll get us in the ballpark. We go to mass properties onto the thing, and they use 7800 and not 7850 right here. What we have found actually is not about the center of mass. This one right here is about the center of mass aligned with the output coordinate system. This one is just taken at the output coordinate system. And so what we end up in terms of numbers here, about the x-axis, we get 6.318. Well, let's double check the mass right here. We have 93.6. That's because we have a difference in the density right here. I could try to override these as I did before, and let's see if that helps. I go 94.2, and say OK. And then, yeah, there you go. See, you got the density is correct. And about here, we get, once again, it's off by a little bit. 6.594 is what I have written down. So I wonder if there's also another mistake somewhere in here. These things should be exact. About the y-axis, so this is significantly off. Well, actually, this one turns out to be correct right here. That's interesting. IXY. But it's actually this one, this IYY, that we should be checking out. And then down below here, the last one, we should have 10.05. Well, this one's correct right here. Okay. Well, that's interesting. I wonder why that we are off by some. Now, in my, let's see, close this off right here. And I can't read this. It's too small. And it was never all that great right here. All right, so this is the one that I did. Yeah, look right here. I got the 4.082 and the 6.594. So I got the exact same thing. I wonder what I have done differently, where I made a mistake in this. It could be the way, did I set up the orientation the wrong way? It could be that, but I don't think I would get that mistake from here. It's interesting. I gotta mess with it, but that's the danger here of trying something live, is that I could show where I'm incorrect. I don't know. Let's see. We did get the, did I ever look for the center mass? I didn't bother looking for the center mass because it was not asked as part of this problem. It's one of the reasons why I replaced this example. I wasn't even going to do this example, but I decided because I already had it written out that I would turn it into a PowerPoint. So anyway, there's another example. Make a table, work through the thing. I know that my my solution is correct in the one that got presented here. It's just my SolidWorks model for some whatever reason. I might mess around with it and find out. But anyway, that's it all for this time. Let's see, what kind of tune shall we play off? I still have my Les Paul out, but let's see. It's oh, you can't really see that right there. It doesn't matter. Ooh, what happened here? Oh, I see it. Turn it should actually try out some of my new amplifiers. I should try out, I bought a couple amplifiers not long ago. I buy a lot of stuff. I can start showing off every guitar in every single one of these videos, and I still would have probably plenty of guitars. So anyway, I take requests. But, I'm not going to sing it, but I do sing that song. That's the Summer of '69, Bryan Adams.